This is going to be the lecture over chapter 21, sections 1 through 3. We're going to be looking here at electromagnetic induction. Now, up to this point, we've been looking at electric fields. We've been looking at what we can do with electric fields in terms of potential, capacitance, and then current, resistance, DC circuits. And then now we've been getting into magnetic fields and forces. But this particular chapter, we're going to take a look at what happens when we start changing the magnetic flux. Now, again, what is the flux? We're looking at the number of magnetic field lines that are going to be cutting through a particular cross-sectional area. And as those lines change, what we're going to notice is that certain types of currents can develop. And not only do those currents develop, they develop in such a way to resist the changing of, or that changing flux of the magnetic field. Nature, it seems, would like to have us have things stay the way they are. It doesn't really want to see it change. What happens is that when it moves through a magnetic field in such a way that the flux changes, that flux is going to create a current, and that current is going to act or move in such a direction to resist that change in the magnetic field. So that's one of the fascinating things about electricity and magnetism that I hope you take with you as you complete this course. So for these first three sections, let's take a look at the summary here. The summary here is that a changing magnetic flux through a circuit loop induces an electromotive force, or an EMF, in the circuit. We're going to determine the initial magnetic flux through the coil in parts of these sections. And that leads us to Faraday's law. And Faraday's law states that the magnitude of the EMF in a circuit equals the absolute value of the time rate of change of magnetic flux through the circuit. So in other words, your magnitude of the EMF, and again, we're just looking at the magnitude, we're not looking at direction, but the magnitude is going to be equal to the amount of change of magnetic flux over time. So the relationship is valid whether the change in flux is caused by a changing magnetic field, motion of the conductor, or both. Basically, it doesn't matter if you're strengthening the field or if you're taking the conductor and you're moving it through the field. It's the fact that the magnetic flux is changing for whatever reason. And it could be both at the same time, but whatever that change happens to be is what's going to produce this EMF. So let's go and let's take a look here. Okay, so we're going to look at some things that Michael Faraday and Joseph Henry did. Faraday was in England, Joseph Henry was in the US. And we're going to look here at some examples. So we've got basically a coil here of wire, and you've got a current measuring device here, like a moving coil galvanometer. When we've got a nearby magnet and it's stationary, we don't pick up any current. Now, think of this almost as the same as whenever you have a constant velocity and you're trying to evaluate forces and any sort of change there. There isn't, if you're looking at constant velocities, you're looking at no change there's no acceleration. Therefore, there's no changing of forces or things like that. Same kind of allegory happens here in E&M, where we're not changing the magnetic field even though one exists. So even in the case where you're moving at a certain velocity, motion is existing, but there's no changing of the force because there's no acceleration. Same type of deal happens here, is that you have the magnetic field present, but there's no change in it. Therefore, in a nearby coil, you're not measuring any sort of current. Now, if you start moving the magnet towards or away from the coil, guess what? You're going to start measuring something. What if you take a second current carrying coil and you've got this current going here and you're moving it up and down away from this particular coil? Guess what? You're going to measure some current. And if you vary the current in the second coil, in other words, you've got a certain amount of current here, you're not moving it, but you're changing the amount of current that's going through. Well, guess what? You're going to end up measuring some current in that other field. These are all going to be induced currents because the result of that current is because of something that's changing on the outside here. And the corresponding EMF that has to be present in order for that, if you've got current, then you've got voltage. And that voltage is going to be referred to as an induced electromotive force, or EMF. So you can see all of the descriptions there, verbal descriptions. Now, if we move on here into a situation such as this, we've got a setup here in which this particular apparatus is looking at induced currents. So we've got a north and south pole for magnetic field here. If we end up varying that particular current somehow, we're going to end up, or that magnetic field somehow, we're going to end up measuring current that is developing in these particular rings that exist within that magnetic field. Here is an application where if you have an induction cooktop, an induction cooktop will not work with non-conducting ceramic or Pyrex cookware. But if you have something that will conduct, then what you're going to see is that you're going to be able to cook, but you can touch this stove and it won't burn you, because we're not talking about a transmission of heat. As it says here, you can set the burner on high and you can place your hand on it and you won't feel any heat. And because this is about changing the magnetic field, which is going to end up inducing a current in cookware. It has nothing to do with heat. It has everything to do with the fact that you're varying magnetic fields rapidly. And because of that, in conducting cookware, it's going to pick that up, and you're going to have induced currents within that cookware, and that causes the pan itself to heat up. Really kind of a neat invention. I wish I could see one of those in person, but have not done that. So that's going to be 21.1. Let's move on to 21.2. All right. So again, we're looking at magnetic flux, and it's the same thing as electric flux. If you remember that, where you have an electric field and you have a certain amount of current, or field lines that go through space in order to be able to hit the target. Like if you have a positive charge and a negative charge, you'll see the electric field that stretches from one to the other. Well, depending on how those electric fields change, you can start to see a certain phenomenon. It's the same thing here with the magnetic flux. Now, magnetic flux is going to be denoted with this symbol, and it's going to be referenced to an area as well as a magnetic field. And you can see the magnetic field lines coming through here. So we're going to take a surface and we're going to divide it into smaller areas. And these cross-sectional areas are going to be referred to as delta A. So for each element, we're going to determine the component of B that is perpendicular to that area element. And from this particular figure, you can, if you took the field lines here, where this is the actual vector of the magnetic field. And if you figure out you want the component that is perpendicular to this cross-sectional area A, you're going to find the angle here, and you multiply by the cosine of the angle in order to be able to produce this value. So the magnetic flux as measured is going to be the perpendicular part of B multiplied by that cross-sectional area of A. And you can see the formula being worked out there. Now, the total magnetic flux of the surface, you're going to be looking not only at just delta A, but you're going to be looking at all the cross-sectional areas and adding all of those up. The units here are going to be Tesla times meters squared, which is the same thing as Newton meters divided by the number of amps. This is referred to as a Weber. The angle phi, that is the angle between the normal to the surface and the magnetic field, which we already went over. And if the surface is edgewise to the field, in other words, if you make it in the same plane as this, forget it, you're not going to get any flux. And that's what this figure is trying to address. If you have your cross-sectional area here A, and it is completely perpendicular to B, then your magnetic flux through here is just going to be the product of those two. If you're at an angle, that's when you apply the cosine here, which obviously in this particular case, the cosine of this particular angle is going to end up being less than 1. So that means that the magnetic flux that you're going to see through that cross-sectional area is going to be a little bit less than the actual magnitude of the field itself. And that's what this is trying to show. And obviously, if this is edgewise on with the field, in other words, it's in the same plane as the magnetic field, forget it, you won't see any magnetic flux. So you've got some problems here that you can go through and work in this particular section. They're pretty well spelled out here. You also have some tutorials here that you can go through, which I would encourage you to do. Now let's move on to section 21.3. All right, Faraday's law. So Faraday's law is going to state that whatever EMF, or this funky looking E here, whatever that is directly proportional to the change in the magnetic flux with respect to time. And it doesn't tell you which direction it's going to go. Faraday's law just says that's what the magnitude is going to be. And obviously, if you're measuring EMF, it's going to be measured in volts. So this changing flux, it can arise from either a change in the magnetic field or the orientation of the shape of the surface. So if we're going to look at an application here, you've got this figure which looked like what we had before. The magnetic field in the region between the poles is uniform to help with the calculations at any time, but is increasing at a rate of 0.02 teslas per second. The area of the conducting loop in the field is 120 cm squared, and the total current resistance, including the meter, is 5 ohms, sorry. So we're going to find the magnitudes of the induced EMF and the induced current in the circuit. So we know that the area here is constant, doesn't change. So the absolute value of the rate of change of the magnetic flux is A multiplied by the rate of change of the magnitude of the magnetic field, magnitude B. So the definition here, and again, what are we looking for? We're looking for the magnitudes of the induced EMF and the induced current. So the induced EMF obviously is related to by this is Faraday's law. So we're looking at the change in B over the change in time multiplied by A. That change is going to be is 0.02 Teslas per second multiplied by the area, which does not change. And this is the amount of voltage that we come up with. The induced current, obviously, if you remember, V is equal to IR. We solve that for I. So we take our EMF divided by the resistance, and we figured out what the current is. Now, remember, if we go back to 21.2, remember how we define the flux. The flux, is B times A. And obviously, if we're looking at the change of this, of the change in time, the area is not changing, then B is the thing that would be changing. And that is why sorry for the flipping back and forth here, but that is why we get this into this. Because again, we're looking for the change in this of the change in time. The area is not changing, and the flux, the magnetic flux, is going to be B times A. If we're looking for the change here, it's going to have to be the magnetic field that's changing. Now, this is going to verify the unit consistency in the calculation. And that's something that when you look back on, you might, when you go through the problem, you might not necessarily think about it, but if you go back through, you want to be able to sort of connect the concepts in physics. Physics is about trying to connect concepts not only from physics 1, which you might have hoped you could have left behind, but this is actually going to build on that. So if you're looking for trying to figure out how the magnetic field and force relate to each other, you can remember that the force is equal to QVB. This is assuming that the velocity and the magnetic field are going to be perpendicular to each other. And if you solve that for B, then you figure out 1 Tesla is going to be equal to 1 Newton divided by Q times V, which, 1 Coulomb times meters per second. Therefore, you can take the units of magnetic flux, which is going to be B times A. This is where the area comes in. So if you multiply this side by that same value here, since this was just B by itself, now if this is B times A, you're going to multiply both sides by the area. This is what you come up with. And if you recognize that a Newton meter divided by Coulomb, in other words, you rearrange this, this, and this, put them all together, that ends up being a Newton meter ends up being a joule. And you can also take the joule per Coulomb here and take that, or Newton meter per second. I don't know why they left the second out there. Anyway, all of that being combined, you get 1 joule per Coulomb, which is the same as a volt. So the unit of the change of the magnetic flux per time is the same as the volt. So you can see here that 1 Tesla meter squared is the same as 1 Weber, so that 1 volt is equal to 1 Weber per second. That's an interesting little connection there. So let's take a look at this. We've got a bar magnet. It's oriented with its north pole facing downward above a coil with 2 turns. What is when the magnet is plunged into the coil? In other words, goes from here to here. A current starts to flow in the circuit, as you might expect, because the magnetic field is changing. This induced current is caused by the change in, you've got the strength of the magnetic field through the coil, you've got the area of the coil, you've got the orientation between the magnetic field and the surface of the coil, all of the above. Correct answer here is going to be A, and I kind of gave that to you as we were working the problem. The strength of the magnetic field through the coil. In other words, you're taking this north pole and you're bringing it towards this. You're having more field lines break that particular cross-sectional area. That's creating your current. So you've got some problem solving strategies here that you might want to go through. You've got some more problems here that you can work. This here is an example of taking a circuit or a piece of wire and having it move through a magnetic field and generating a current. That is a good problem to work through. Now, generators. A generator, as you might expect, is a device that's going to convert mechanical energy into electrical energy. So a common design is going to be a conducting coil that rotates through a magnetic field, something like this. It's going to produce an EMF according to Faraday's law. So we've got a rectangular loop with area A rotates with constant velocity omega. So this area A rotates through. And as it rotates, the magnetic flux through it changes sinusoidally with time, inducing a sinusoidal varying EMF. So if the shaft of the coil is connected to a windmill, it's going to convert wind power into electrical power. So the magnetic field is uniform and constant. So at time t naught, or time t is equal to 0, phi is equal to 0. And the loop, the figure shows the loop at the position 90 degrees. So if we look at a generalized form of Faraday's law, we're going to assume here that the EMF, magnetic flux, and the change of that flux with time can be either positive or negative. As it rotates, the sign of both E and the magnetic flux reverse twice during the revolution because of how it's rotating and how it's cutting those lines. So the flux through the loop equals its area multiplied by the component of B perpendicular to the plane of the loop. In other words, B times cosine of theta. This changes how? How does that change? Well, it changes by the angular velocity multiplied by the time. Just like linear velocity multiplied by time is going to give you the distance, this is the same thing with that particular angle. Now, this and this can be positive or negative as we make our changes. Because it's sinusoidal, this isn't constant. So we derive an expression that would require calculus, which we're not going to do here. As it turns out, this ends up being that the EMF is equal, of course, to minus the change in the magnetic flux with respect to time, which ends up equaling this. As you plot this loop as you go through, you can see here the EMF with respect to time and how it changes. This here is the magnetic flux. This is the change of magnetic flux with respect to time. You can see how these two move in tandem. They're just a little bit out of phase with each other. So we can use a similar scheme in order to obtain the EMF and make sure that it always has the same sign. The arrangement is going to be called a commutator. It reverses the connections to the external circuit at those angular positions where the EMF reverses. The result is the figure shown in 2021b. So in other words, rather than having it run negative, it's now going to run positive. And so the resulting EMF, this is the prototype of the direct current or DC generator. Commercial DC generators have a large number of coils and commutator segments. And so this arrangement smooths out the bumps in the EMF. So the terminal voltage is not only unidirectional, but also practically constant.